Hello friends, welcome to the class of marketing research and analysis. In the last lecture we had started with the concept of covariance and correlation, where I explained you what is basically the utility, the use and the meaning of covariance and correlation, how correlation is a much powerful technique over the covariance, the reason behind it, and I said that covariance is slightly becomes awkward due to the units that it uses for two variables. That means, two variables could be having very different units, and that sometimes looks very difficult, very absurd to compare, and that is why we need to have another technique which can standardize them and give us a solution, so that it is easier for us to compare, right. So, covariance was basically telling us about the direction and not the degree or intensity, whereas correlation on the other hand tells us both the degree and the direction, right. So, that is the advantage. So, we will proceed with today's class with the correlation. Okay. So, how do you study correlation? So, basically the from a visual point of view, you can have a scatter diagram method or a graphic method, right, or we have a Karl Pearson's correlation of coefficient and method of least squares, right. So, these are the ways you use to measure the correlation or check the correlation. Now, what is the scatter diagram? Scatter diagram method is a very simple method to study the correlation between two variables, wherein the values for each pair is plotted on a graph in the form of dots, whereby obtaining as many points as the number of observations. Then by looking at the scatter of the several points, the degree of correlation is ascertained. That means, it looks something like this. For example, if I plot certain dots, for example, these are the dots, right. So, dots are each my observations, right. So, from here let us say this is my x and this is my y. So, can I say what kind of correlationship exists? So, if I draw a line in between, so I can say, well, there is some positive correlation, it is increasing, it seems, right. But suppose I have another relationship something like this. Okay. So, here if I draw what is the correlationship, it is very difficult to ascertain, because it is in fact there is I can hardly say there is any relationship. So, scatter diagrams help you to visually understand that, but they are unable to give you the exact extent of correlation, how much, which is the most important part of correlation is the how much, that how much is what you do not get here. This chart does not show you the relationship for more than two variables, only two variables x and y, but not if there are three variables multiple correlation, you can't do it. The degree to which the variables are related to each other depends on the manner in which the points are scattered over the chart. Yes, that is true. How they are scattered, is there any pattern or not, that decides. Okay. The more the points plotted are scattered over the chart, the less is the degree of correlation. That means, if the spread is too large and it is in a unsystematic pattern, then the correlation is weak. The more the points plotted are closer to the line, that line which I said, suppose this is the line, right, the higher is the degree of the correlation. So, the closer they are to the line, right, the higher is the degree of correlation between the two variables. It is denoted by R. Okay. So, this is you see the perfect correlation, positive correlation, where R is equal to 1. So, R is equal to 1, weight, and we have taken height. So, when we are saying it is a positive perfect positive correlation, right. When R is equal to 0.8, when we have measured R, we will see how to measure R, but when height and weight we are saying the R is equal to 0.8. So, we say it is a substantially strong positive correlation, it is a positive because of the sign and because of the value lies between -1 to +1, right. So, it is close to +1, so positively highly positive, moderately positive now. So, this is somewhere sign is positive and 0.4. Now, if I draw a line, you see, so this looks little awkward, but still it is a positive correlation. Okay. Now, this is a perfect negative, you see, TV watching per week and scores in the exam, right. So, my relationship is negative, as my TV watching is high, my marks are low, as the TV watching goes down, my marks are increasing, a perfect correlation, but the direction is inverse, negative relationship. That means, if one increases, the other decreases. Okay. Moderately negative similarly, so -0.8, right, no correlation. So, here you see IQ and height, is there any relationship with IQ and height? Well, if I draw, what is the correlation coming? Nothing. So, the best method of measuring statistically is called the Karl Pearson's method of coefficient of correlation, right. So, this is also called as product moment. You must have seen somewhere written as simple correlation or product moment correlation, right. It gives a precise numerical value of the degree of linear relationship between two variables x and y. So, what is the degree of the relationship? And this relationship may be given by a regression equation, which is y is equal to a plus b of x, where y is my intercept, b is my slope, okay, and x being my independent variable. As I said, it lies between -1 to +1, right. Okay. So, this is how, this is the formula. So, how do you measure the Karl Pearson's coefficient of correlation? The formula is very simple, you need to understand. So, what we said, correlation is a standardized form of the covariance, right. So, if my covariance value, if I divide my covariance value between x and y with the standard deviation of x and standard deviation y, this is what it becomes as the my coefficient of correlation. So, if I break it, how does it look like? Xi minus x bar, right, is the covariance for covariance value into yi minus y bar. So, yi is the observed value, yi and the xi are the observed ones, and x bar and y bar are the corresponding means for x and y, by root over of formula for standard deviation is x minus x bar square into root over of y minus y bar square. The n minus 1 here and the n minus 1 here actually are cutting each other. So, that is why we are not showing, it is not required anymore, right. So, this is the way you write, this is a very simple thing, you just remember this much and nothing, you do not have to remember any other thing, okay. This is another way of representing the same thing, okay. So, let us see. So, interpretation of the correlation coefficient, the value, okay, this is said, right, if it is +1 perfect and positive, if it is -1 perfect and negative, if r is equal to 0 no correlation, okay. Some assumptions in correlation, what are the assumptions? The variables should be measured in the interval or ratio level first, they should be continuous, okay. For example, time, revision time, intelligence, exam performance, weight, okay. There is a linear relationship between the two, the assumption, this is an assumption in correlation that the relationship is linear. While there are a number of ways to check a linear relationship, creating a scatter plot against each other and then visually inspecting is the simplest way, right. So, you see if I draw a line, you see I draw a line, here also I draw a line. So, these two are non-linear, but this is linear. If the relationship displayed is not linear, you will have to either run a non-parametric equivalent to the Pearson's correlation. What is a non-parametric equivalent? I have explained it earlier also when I was teaching non-parametric techniques, in which I said there is a technique called Spearman's correlation, right, which is used as a non-parametric test for the correlation, okay. So, or you have to transform your data and convert it from into a normally distributed data. If it is non-normal, you have to convert it to a normally distributed data. And if normally you distribute, the data is normally distributed, the chances are very fair that it will follow a linear pattern, okay. The third assumption is no significant outlier should be there, okay. If there is an outlier, it will distort the entire situation, okay. Fourth, the variable should be approximately normally distributed in order to assess the statistical significance of the correlation. Now, what does it mean? If you do not have understanding whether it is statistically significant or not between the relationship between two variables, then although you get a degree, you cannot say it will happen every time the same way. Maybe it has happened this time by chance, but maybe another time it will not give the same result. So, but if it is significant, that means it is not by chance, it will happen again and again and again in the same way, right. So, but this method is okay, difficult to assess. So, a simpler common method is used. This method involves determining the normality of each variable separately. So, what it says is you do not check it at the same time, but individually you check whether the data or the variables are normally distributed or not, okay. What are the limitations of Pearson's coefficient? Does it have any limitation? Yes. First of all, assuming a linear relationship in life, I said earlier ki most of the relationships may not be linear, they could be non-linear. interpreting the value of R is sometimes difficult, although we say if it is +1 it is extremely positive, -1 extremely negative, but it is still interpretation is a little challenging. They are affected by the extreme values outliers, and they are it is slightly time consuming to calculate and understand, because in real life nothing comes in a plate to you, right. So, suppose a situation is given and then you have to interpret what are the variables and then find out what the relationship is not that simple as it looks when I give you on a pen and paper, right. Now, let us solve a problem. Find the correlation coefficient between the sales and expenses from the data given below. So, sales is given 50, 15 number of maybe different firms are there, firm 1 to firm 10, and the sales is given 50, 50, 55, 60, 65, it goes on. This is all in millions. Okay. The expenses conducted by this or expended by these companies are 11, 13, 14, 16, 16, 14, so something. Now, I am interested to know what is the direction of the relationship. Is it a positive relationship or negative relationship, or there is no relationship, and what is the degree of intensity of the relationship, how strong is the relationship. So, to do this if we cannot we will not do a a covariance, right, we will do a correlation in this case, right, and luckily these are having same units also. So, let us say now how do we go about it. So, these are my firms. So, there are 10 firms, sales is given. So, my summation of the sales is 580, summation of my expenses is 140. Now, I need x minus x bar. So, what is the formula? Covariance by standard deviation of x by into standard deviation of y. So, first we find out x minus x bar. So, x minus x bar, x minus x bar is how much? 580 divided by 10. So, this is my x bar, my y bar is 14. Okay. So, x minus x bar minus 8, 55 minus 58 minus 3, 60, it goes on, right. So, this total is 0, right. Similarly, if you look at y minus y bar, right. So, y minus y bar is again 0, right. So, because they adjust each other, right, but for that we will take the x minus x square now, right. So, what is the x minus x square? 360, and y minus y square is 22. Now, the product deviation of x minus x bar into y minus y bar. Now, this is equal to if you multiply 8 into let us say 3, 24, 8 into 1 8, minus 3 into 0 0, so goes on 70. Okay. So, what is the formula? X minus x bar, how much it has come? Let us check. So, x minus x bar into y minus y bar. So, this is 70 divided by x minus x bar square. So, x minus x bar square is how much? X minus x bar square is 360 and this is 22. So, root over 360 into root over 22. So, this is equal to 0.787. So, my correlation between the sales and expense is, first of all, is it positive or negative? It is positive. Okay. And that means if sales increases, expenses, if expenses increases, my sales increases, right, and it is 787 means it is close to 1. So, it is a high. So, there is a high degree of positive correlation between the two variables, that is, as this value of sales goes up, the expenses also go up. Okay. Now, I will show you how to do this in the SPSS. Now, this is a case where a researcher wants to know whether a person's height, okay, this is an example I have taken, but I will use a separate example in this case just to show you how to, what are the steps. So, what you do is you go to analyze, go to correlate and go to bivariate. Okay. After going to bivariate, you take the bivariate. Why it is called bivariate? Because there are two variables, bicycle, two wheels. Okay. So, height and suppose the jumping distance, in this case it was in this example. So, and what is the tail, and you have to take, right. So, then you have to go for this and you have to see whether you require the mean and standard deviation or not, all these things. Okay. And let me show you here, first let me show you, then we will try to analyze. So, let me take this case. Now, what I have done is, this case is a case where we have taken values of the correlation, we want to find out the correlation between body temperature and the heart rate, the heartbeat rate. Okay. So, these are some of the values for around 120 people I think. Okay. So, 130 people in fact. Okay. So, if I want to see what is the correlation between is there any association between body temperature and heart rate? I want to check that. So, to do that, how do I go into SPSS? Now, first I will go to analyze, I will go to correlate and then go to bivariate, right. So, I want to take my both the variables body temperature and heart rate, right. In options if you go, you can go for means and standard deviations if you want, right, and other things remaining the same. Now, let us see, is there any relationship between the two? Now, body temperature, with body temperature the correlation will always be 1, is the same thing, because, and body temperature and heart rate the correlation is 0.254. But interestingly, the important thing is it is significant. Significant at what? Double star shows it is significant at 0.01 level, right. So, you can see here 0.004, which is much less than 0.01. So, the null hypothesis is rejected. What is the null hypothesis? In the case of correlation, you should be able to always write the null hypothesis. The null hypothesis is that there is no correlation or there is no relation between the variables, right. So, this null hypothesis has been rejected. So, what is the null hypothesis? Alternate hypothesis, that there is a relationship between the variables. Now, positive or negative, that is separate, but there is a relationship. Okay. Now, look at the body temperature mean and standard deviation. If you want to use this data, you can also use this. Okay. Now, another example we have, this is I think you have understood. Now, let us take this one. Now, somebody wants to see whether there is a relationship between the amount of distance driven and the number of accidents happening by let us say a bus service provider. Okay. Now, let us see what is the relationship coming here. So, I am taking two variables, number of casualties that is happening by let us say a particular bus service organization and the number of billions of kilometer or kilometer they are driving. Okay. Now, if you look at the output, we will go to the output and you see here the correlation between the two is 0.157, but interestingly if you see the significance value, it is 0.253. So, what is happening? This 0.253 is much above the designated value of 0.05 or 0.01, which we generally take as a significance level value. So, the null hypothesis cannot be rejected. So, what is our null hypothesis? That there is no relationship between accidents and the amount of kilometer driven, and yes, that is acceptable. That means you cannot say ki there is any relationship between the two, right, you cannot claim that, right. So, if I want to show you how this would have looked in the scatter diagram, because some people wanted, I have explained scatter diagram. So, I will explain how you show this in the scatter diagram, this relationship. Now, go to this chart builder or legacy, right, and go to scatter plot here, go to the simple scatter. Okay. Now, take body, what is your heart rate? Heart rate is my dependent variable. So, I am taking my heart rate as my dependent variable, my body temperature as my x axis, my independent variable. If you want to give a title to this, you can give it. So, suppose some title you want to give, you can write here, right. Now, I want to just see it, how does it look. So, let us go to the output file, and if you look at it, this is how the variables are scattered, the variables, whatever variables you have, the data, sorry, not variables, the data are scattered. So, my two variables are body temperature x axis, heart rate y axis, and this is my how the data is distributed. If you look at this data and you want to understand, then you may be able to understand, but still to make it more clearer, let us do one thing, make a double click on this. Okay. Now, if I make a double click, then what I do is I will go to this fit, there is a total fit, right. So, when I go this, I draw a line, it draws a line which now helps me to understand the distribution of the data around this line. Okay. And if you see here, something is written called R square. The R square value is something which I will be explaining you later, called it is called the coefficient of determination. Okay. So, this R square is equal to how much? Now, 6.4%. Well, so this tells me ki well there is some kind of a, if R square is 6.4. So, what is my R? The R you can just say root over of this. So, that means something around, let us say how much it will be, R square is 6.4, root over of 6.4 is 2.5 or more than that, right. So, that is you can find out the relationship between R and R square, and thus you can say the correlation value is this much. Okay. So, this is what this is the use, okay, of this the scatter diagram. Okay. So, it helps you to give a visual look. So, output for Pearson's correlation, how it is running in this case you see. So, height, suppose in this is just a fictitious example, height and the jumping distance, the correlation was let us say 0.706 and it is significant. In this example we can see that the Pearson correlation coefficient is 0.706 and it is statistically significant at 0.05 or it has taken 0.005, but usually it is 0.05, okay, 0.05, that means 5%, right. So, that is what it says. Okay. In our example, what is this coefficient of determination? That is what I just said, R square, right. The convenient way of interpreting the value of correlation coefficient is to use the square of coefficient of correlation, which is called coefficient of determination. So, the coefficient of determination is nothing but this R square. So, if R is my 0.9, R square is my 0.81, right. So, similarly, if I had a R square of let us say 0.064 in my case. So, what is my, if this is my R square, so what is my R? This is equal to 64 by let us say 1000, right. So, root over. So, 8 by let us say how much it is 33, let us say 33. So, that is somewhere around you can say, so whatever it comes, right. So, root over this value is equal to 2 point something. So, that is what I was saying 2.5 or 2.4 whatever it comes, right. So, this is my R value, right. So, 0.24 or 0.25 whatever it is, because it cannot be more than -1 to +1, it has to range in between that, right. Coefficient of determination, the maximum value is 1, right, because it is possible to explain all of the variation in y, but it is not possible to explain more than all of it. That means what? If my R is 1, so R is equal to 1, so R square also can be 1, right. So, explained variation, coefficient of determination in regression also I will show you, it means what does it mean theoretically? It means it is the ratio of the explained variance by total variance. Now, what is this total variance? Total variance is equal to explained variance plus unexplained variance, right. So, this is my total variance. So, here I am saying coefficient of determination or R square is equal to EV divided by EV plus UEV, unexplained total variance, unexplained variance. Okay. So, this is what it says basically, theoretically this is the meaning. Okay. Suppose R is equal to 0.6, R is equal to 0.3, it does not mean that the first correlation is twice as strong as the second. The R can be understood by computing the value of R square. Now, let us see R is 0.6. So, what is my R square? 0.36. Second case, if my R is 0.3, what is my R square? 0.9. So, here it implies that in the first case 36% of the total variation is explained, whereas in second case 9% of the total variance is explained, which is almost, this is 4 times, not 2 times, right. From a visual here you could have thought it is 2 times, but actually it is 4 times. The explanation that it is giving you is 4 times, right. So, well, what I will do is, there is another method, this is for the coefficient of correlation you have understood. There is another technique which is also used for a non-parametric data, and this test is called a Spearman's correlation, which is called as Spearman's rank coefficient of correlation, right. I have already done it earlier also, but for the benefit of many of the viewers who have not followed that, I can just brief you. So, this Spearman's rank correlation coefficient is nothing but a study in which the data is in a non-parametric nature, right. So, in which the variables are not capable of a quantitative measurement, but can be arranged in a serial order. So, they do not follow a normal distribution because they are not in a continuous order, manner, they are not collected in a continuous manner. So, that is one of the assumptions, that it should be in a ratio or interval scale for a correlation, but here it is not in a ratio or a interval scale, rather it is in a order, that means in a ordinal scale. Okay. In such situation, the Pearson's correlation coefficient cannot be used, right, and we use the Spearman's correlation. So, this is the formula 1 minus 6 summation d square, where d is the difference in the ranks, divided by n into n square minus 1. Okay. So, this other things remaining more or less the same, right. So, let us see how do you do it. Now, calculate the difference d of 2 ranks R1 minus R2 and square the difference and calculate the d square. substitute the values obtained in the formula that was shown to you, right. Problems where ranks are not given to you. If the ranks are not given, then we need to assign ranks. If ranks are not given, just assign ranks. So, by maybe the number, the score of somebody or something, you can assign ranks, right. The lowest value will be ranked 1 or the highest value can be ranked 1, whatever order you want to take. We need to follow the same scheme of ranking for the other series also. Suppose there are two variables 1 and 2. So, if you are using in ascending order for one, please use the ascending order for the other one also. If you are using descending, use descending for both. Then calculate the rank correlation coefficient. Okay. So, this is the formula, right. Let me take a if I have, what is the limitation of this? It cannot be used for finding out correlation in a grouped frequency distribution, and this method should be applied where n exceeds 30. Now, this is the case. A ranking by manager 1 of several employees A to J, there are 10 employees, right. Manager 1 gives these ranks to these people, manager 2 gives this ranks. Suppose it would not have given rank to you and it would have given you, let us say, some score, let us say 35 to 38, 40, 41, 44, so 36. So, what you could have done is you could have made them a rank. How? Now, for example, I am starting with the lowest, let us say 1, let us say 2, let us say 3, 4, 5, 6, right. So, this is how you do, right, and manager 2 also has given some ranks. Okay. Now, this is the rank by manager A1, this is the rank by manager 2. So, I am finding the D, the difference between the two. Now, the difference between the first one is 1. So, I will take 1 square, 2 minus 4, so minus 2 square 4, right, 1 minus 2 1, it goes on. So, my D square is 14. If I have my D square, we know that R formula for the Spearman's correlation is 1 minus 6 sigma D square by n square minus 1 or n cube minus n. This is hardly it makes a difference, it actually does not make much of a difference at all, right. So, if I do this, it is coming 0.915. So, we say thus we find that there is a high degree of positive correlation in the ranks assigned by the two managers. So, why it is helpful? Because it is helpful that it says the two managers are thinking alike, right. So, if you thinking alike, otherwise we would have said the managers are thinking differently. Okay. So, this is about the Spearman's correlation. So, earlier we discussed about the Pearson's correlation, we saw how to do the Pearson's correlation, and we also saw how today how to do the Spearman's correlation for a non-metric variable or non-metric data, right. So, this is all for the day. Thank you so much.